All right, welcome back everyone. So we're going to move on to a new topic, and this topic goes along with our stresses we've covered so far, but now we're going to start talking about a torsional or twisting stress. So let's start with a brief review of what we've covered so far with this idea of stresses. So the first type of stress we talked about looked like this, where we said we could have an object just in tension or compression, a pushing or a pulling. We said if we do that, if I were to draw a little section in here and say what's going on in the interior of this little bit, what we call that is the stress. And in this case, the stress was going in the same direction here, and we called that sigma. And we had an equation, and we said sigma was equal to the force divided by the cross-sectional area. So what we have is, if I were to cut this member, the stresses are all perpendicular to the cut, right? If I were to cut right through here, it's perpendicular to that. Then we said, well, what would happen if it were parallel to that cut? So this is what our loading looks like. We call that a shear force. And from that, just like before, I could just look at part of it, right, where that little cut is. And from that, I end up with a shear stress all along this face, which we were calling tau. And we said that tau is equal to whatever the shear force is over the cross-sectional area. So we've looked at our object and we've pulled it and we've cut it. Now what we're going to do is twist it. And this is called torque or torsion. So let's take a look at what happens if we twist it. So I'm going to do my best to draw this in 3D, not always an easy prospect. If we had this shaft, in essence, attached to the wall, and then I apply a torque on it, so what it means is I'm twisting it around like this, and we call that torque. That's where we start to develop this stress. Now we have to define some new variables. We're going to define the diameter. Now we're going to only do round sections. I know I keep picking up this one, but really all we're going to be looking at is round sections. But with that, we're going to define that diameter as being 2c. And I know we haven't talked about this value of c yet. And what c is, it is the distance from the center to the outside fiber. Or really all that means is it is the radius, right? Because here's the center of it. If I were to draw like an axis coming out here, there's the center of my circle, and the distance from the center to the outside is this distance here, which we're calling c, right? So why don't we call it r? Why don't we just call it the radius? The reason we don't is because we could have different shapes. If we were going to look at this, the c value would be from the center out to this corner, so it would be slightly different. Also, in a little while, we're going to talk about bending stresses, and we'll have this value c again. So c is just a generic term that means from the center to the furthest distance away from the center, right? Now, we're also going to define a distance away from that center in a more generic dimensional term, meaning the distance going in this direction outward, we're going to call that goofy looking p, which is actually a rho. So rho is the radial distance away from the center. So what happens as far as when I'm twisting this thing, as far as my stresses, if I were to draw a section right through here, since we've always been looking at what's going on through a cross section, what I end up is with something like this. And you can probably imagine on the two sides I have stresses that are going equal and opposite direction. And because they're going like parallel to the section, meaning the section is like if I just lopped it off, they are considered a shear stress. So as I move from one side to the other, it is actually linear, meaning my stress is decreasing, my shear stress, as I get closer and closer to the center, and it flips directions, and then it goes all the way out to the other side, right? And I end up with something like this. And we said we have this new coordinate rho, which is from the center outward. And we also said we have this distance from the center to this outside part, which we called c, or the radius of this whole thing, right? So from this, you can already see that the highest shear stress would be on that very outside edge of it, the outside fiber at point C. So what we need to do is we need to have an equation to figure out what that shear stress actually is. And so here is, I'm just going to give it to you, we're not going to derive it or anything, but this is our shear stress based on the torque. And this is also known as the torsion formula. So the equation for this looks like this. We have our tau, and we used tau before. Remember, we used this tau for our shear stress. Well, this is still a shear stress. We use the same variable, same idea, but instead of having this type of force, we're twisting it. And we have our tau is equal to the torque that I'm applying. That was this bit right here, right? That's our torque, times rho, which is our distance away from that center point, which gets greater and greater the further away I get away, divided by this value J. J is called the polar moment of inertia, and I'll define that in a little bit. Don't let it freak you out. It's actually a pretty easy concept. So in general, that's our general formula. Now I can also say that the maximum shear stress, which is what we're almost always concerned with, will be equal to the torque times the furthest distance away is C divided by J. So exact same equation, except I'm replacing the rho with a C because we're saying the shear stress on the outside fiber, which is C, right? So what are these variables? Like I said, T is our torque, and C is that outside fiber, and then this J. And J is called a polar moment of inertia. And while J could have several different equations based on the shapes and everything, like I said, we're only going to have one shape, and that is a round cross section. So let's talk about how we find that value J. So let's start with if I have a solid shaft. So of course a solid shaft and a cross section would look like that. I'd have a radius, which we already said is C, and the equation for J is equal to pi over 2 times this C value to the 4th power. So it's just an equation, you just have to plug it in. Almost like the area of a circle. Instead of pi r squared, we have pi times C to the 4th, and then we're also dividing by 2. Now, similar to area of a circle, you might remember, you probably always learned it was pi r squared, but in this class we said, well, let's use pi over 4 times the diameter squared. And the reason we did that is because we always know diameters, we never know radiuses in construction. It's the same idea here. So what I can use is I can use a different formula if I want for J, up to you, but I have to change this little factor in the denominator. So instead of pi over 2, I'm going to have pi over 32, and that's going to be times the outside diameter to the 4th power. So whatever floats your boat. A lot of times the diameters will be given, so that's a little bit easier, right? Now that's for a solid shaft. The only other thing that I think we might want to know is for a hollow shaft. So if I were to draw a picture of a hollow shaft, now I have something with a wall thickness to it. Like these would be your pipes, drive shafts, things like that, right? So with this I have two different C values. I have the inside radius and the outside radius, right? So I'm calling that CI and CO. Well, the equation looks almost the same as what we just did. J has the same pi over 2, but now I have parentheses, and I have to say the outside radius to the 4th power minus the inside radius to the 4th power, right? Or, like we said, if I want to work in diameters, I would have pi over 32 times the outside diameter to the 4th power minus the inside diameter to the 4th power. So let's go ahead and take a look at an example on using this new torsion formula. Okay, so here's our example. Let's say we have a 1.5 foot long shaft, and it has an outside diameter of 6 inches and inside diameter of 4 inches. So it has a wall thickness, well, that should be a question for you, right? That'd be a great multiple choice. Is the wall thickness 2 inches? No, the wall thickness is only 1 inch because we'd have one on each side, right? If the shear stress should not exceed 120 psi, what is the largest torque that the shaft can hold? So I drew a little diagram here, and I'm showing the radiuses. So I divided those numbers by 2 to get the radius from diameter. Could have worked all the way in diameters. I just thought it was easier to draw the picture like this. I'm going to go ahead and start this problem. Well, actually, if I were you, I'd push pause and see if you can solve this on your own. All right, since you either did it and you want to check it or you skipped over that, I would start by finding this polar moment of inertia. So I'm going to do it in diameters. You could do radius as well. At diameter, we said it's pi over 32 times the outside diameter to the 4th power minus the inside diameter to the 4th power. So hopefully you know how to punch that into your calculator. I did it on my iPhone. There's a little caret symbol you can use. And when I plug that in, make sure you get your parentheses in the right place and all that business. It's just a matter of calculator skills, right? I ended up with 102.1 inches to the 4th power. And what it's saying is we have a maximum shear stress. So I know the maximum shear stress happens on that outside fiber, right? So it's when that rho value is equal to C. So I'm going to use the equation that says tau is equal to TC over J. I mean, you could always use T rho over J. It's just you know, letters, right? So you can sub in different things. And then I'm just going to plug in these values that I have. So I have the largest possible shear stress is 120 psi. So that's my tau. And that'll be equal to the torque, which is what I'm looking for, times C. Well, what is C? C is the distance from the center to the outside fiber. In this case, so it would be that 3 inches. And dividing it by this J value, which I found to be 102.1 inches to the 4th power. You can follow your units and multiply through and solve for torque. It's just algebra if you get stuck with some of that. It's just 120 times 102.1 divided by 3. And I ended up with a torque of 4,084. And the units would be pound inches, which should make sense, right? So if you've ever dealt with torque before, it's like a lever arm type thing. So it's almost like if I were looking at the torque on this object here, if I had a longer lever arm, call this L, and I had a force down here, my total torque would be force times that lever arm L. So of course, if I have a greater force, I have a greater torque. If I have a greater length, I have a greater torque. But that means for my units for torque, I will always have a force times a distance, right? So in this case, what I have is my forces in pounds, my distances in inches, and I end up with a total torque of 4,084 pound-inches. Now for part B for this problem, let's say that we wanted to know the shear stress at the inner surface. Like say there was a crack on the inside right here, and we wanted to know what was the shear stress at that point. All right, so that's what I'm looking for written out. I have this TC over J, and I could use T rho over J. It's just a matter of getting the right value in there. Now we're saying what is the shear stress? So we're solving for that tau. The torque I already found to be 4,084 pound-inches. And then our C value is that distance from the center to where we're looking. In this case, it's the inside surface, so it would be 2 inches. Over the same polar moment of inertia of 102.1 inches to the 4th. So punch that into your calculator. I ended up with something like 80, and then my units would be, and you could follow your units here because I have this inches with that inches gives me inches squared. So this becomes inches squared on the bottom because 2 on the top cancel out 2 on the bottom, and then I have pounds on top, so I have pounds over inches squared, which is the same units we've been using all along when we say PSI, pounds per square inch, when we talked about stresses. So now we have a shear stress on the inner surface of 80 psi, and a shear stress on the outer surface would be 120 psi. So that's what I have for an example. I hope you found that helpful. And if you look at the posted notes, there is a second example on there you can see as well. But I figured to keep this video a little shorter, I'd just do one example on here. So let me know if you have any questions or comments, and I'll talk to y'all later. Thanks.